Thanks very much, Ben, and thanks to Jishin and everyone else who's put this together. It's a real pleasure to be here and to celebrate John and to chat with you all. So I'm usually at Griffith University, but I'm currently on leave of absence. I'm working with PsiQuantum. I'm not going to talk about PsiQuantum work today. If you are interested in PsiQuantum presentations, hopefully you saw Jeremy's at the AIP Congress recently, but if you didn't, no problem, because he'll be back in Sydney soon for the Quantum Australia meeting that Pete was advertising. So come along to that next month and you'll hear updates from what's going on in PsiQuantum's approach of building a quantum computer. So today I'm going to talk about work that's done at Griffith University, and I'm on leave of absence. So the people who are running the show, Quantum Optics is in good hands at Griffith, because it's not just me there as an experimentalist, but also Nora Tischler, who's an assistant director at Center for Quantum Dynamics and is also here, and you've heard her speak. And also another senior research fellow, Sergei Slusarenko, and you'll hear about a lot of the work done today has been done by Sergei. So I first met John in the early 2000s when I was a postdoc with Andrew White. And so I realized that I was actually a sort of junior co-investigator on a US Army and intelligence quantum computing grant with John and a bunch of other people, some of whom are here today and at this meeting. And they were some good times learning from John about quantum computing, amongst other things. One of the other things that is my earliest memory of John, though, I think, from those days was listening to some of his talks. And we've heard from Mark and others about, the High Noon posters and the Wizard of Oz cartoons and all the other parts of it. But another aspect of John's talks was that he'd often pick out somebody from the community, often an experimentalist, maybe Paul Queert or Andrew White, in fact, and just choose that particular talk to make fun of them mercilessly. He just sort of, make fun of where they were from, the way they dressed, their accent, the fact that they were stupid experimentalists and didn't know anything, and so on and so on. And as a junior sort of postdoc, it was fun to see your boss be sort of thoroughly humiliated in front of hundreds of other people. Although, Andrew being who he is, he took it pretty well. But those were the days. The other time, apart from talks, that I spent time with John, of course, was in restaurants and bars. And my first international trip after COVID and after John passing on, I flew into San Jose and saw the Gordon Biersch, or as John would say it, Gordon Biersch place in San Jose, and remember the many times that we've sort of spent, drinking beers and having meals there. It was also in a restaurant in San Jose that I remember coming across John's legendary generosity, and particularly to younger people. I was pretty junior back then. I'd just gotten my faculty position at Griffith University, which was good that I got that because I had 3 young kids and sort of needed to feed them. And, salary wasn't that good, but, I'd say at least it was a continuing position. So that was nice. And we were at this conference, and John and several of us went to this restaurant. And John was the senior person there, and everyone else was junior. In fact, most more junior than me, postdocs and PhD students from various groups. And we had dinner, and then we started to drink, the cognacs and the Armagnacs and the things that John liked to drink. And he was impressing us with his knowledge of all these fancy drinks, and we were spending more and more and more money. And it got to the end of the night, and, you won't be surprised to hear that the bill was quite large. And John said, well, there's a lot of junior people here. You shouldn't have to pay for it. I thought, oh, wow, this is so generous of John. It's amazing. And he said, well, Geoff and I are faculty, so we'll pay, split the bill. Thinking, got 3 small children. Oh, well, they're young enough. They won't remember if they miss a few meals. It's fine. But in all seriousness, John was, in fact, very generous. And I was the beneficiary of many of his reference letters written over the years and asking only to pay it forward. So. All right. We're not going forwards here, Dan. Oh, here we go. Okay. So today I want to talk not about quantum computing, but about the other area of photonic quantum science, which John, of course, was very big into in those days, which was metrology and noon states. I'll then go on to say a little bit about the internet. So let's talk about some more up-to-date stuff as the talk goes on. But I remember, coming into the field at the time where Peter and John and others, were really making waves with their approach to the high noon stuff. And that's what I've called quantum metrology the old days. But let's have a look at this. One of the results that Howard and Dominic and I looked at in 2006 was this idea of thinking about the phase estimation problem from first principles. So thinking about not just sort of sitting on a fringe and seeing how one could accumulate data, but saying we knew nothing about the phase. And there'd been previous work saying, the noon state is this parallel kind of entangled approach to looking at things, but one can do sequential measurements of the phase shift, and perhaps even in multi-rounds with adaptive measurement and things like this. And this was the problem that we went off and looked at. And we came up with some interesting things. We looked at, how this compares to the Kitaev phase estimation algorithm, what you need to do differently given what the tails of the distribution look like, how you can do Bayesian updating in the adaptive measurement and all this kind of stuff. And we published this paper, and I was going to tell you a little bit about it, but since it's ancient history, you don't want to know about it. And I can tell you that it's ancient history because this is what PowerPoint gave me when I pulled it up. So if PowerPoint doesn't remember, let's just move on, right? Anyway, so this paper was published, and I was interested to know what John thought of it. And the very next year, or I should say this term entanglement free is going to come up in a moment. So just focus on that. I was interested to know what John thought of it. And the very next year, of course, he published his contemporary physics paper. And it started off with a really nice description of the work we'd done. At this point, something came out of the sky like a bolt from the blue at high noon, another Australian collaboration, blah, blah, blah. Went on to say some nice things. But I was a little bit suspicious because he used the name Jeffrey, which is, only my mother calls me Jeffrey. So I thought, okay, maybe I'm in trouble here. And indeed, he did in fact have a bone to pick with us. And it was around this term entanglement free, right? I mean, we were putting single photons into interferometers, and John pointed out, well, when you put a single photon on a beam splitter, as Austin was reminding us yesterday, that is indeed an entangled state. But very graciously, John went on to say, oh, maybe they meant it was unentangled before the beam splitter. And I thought, phew, we escaped, but didn't escape for too long, because that very same year there was a conference in Cairns where John was presenting, and now it was my turn to be the butt of all the jokes in the talk. Geoff doesn't know what entanglement is, and so on and so on. And so while I was being pulled apart in that talk, I thought I was having a bad day, but it turns out someone else was having a bad day, because John started to reveal, well, in actual fact, I refereed your paper, Geoff, and so inappropriate, but nevertheless telling us all about refereeing our paper and how he did, wanted to accept it and so on. But then he turned to Carl Caves, who was in the audience, and said, oh, Carl, I also refereed one of your papers this year and I rejected it. Carl was furious, as you can imagine, and Nick was telling me yesterday that, Carl's never forgotten that. So, so we laugh here, but, don't tell Carl I said that. Anyway. The thing about these early noon experiments that we did, and that we heard about in John Rarity's talk and so on, is that they were all only violated the shot noise limit or showed Heisenberg limited scaling or something in some conditional sense. The Mandel and Kuzmich paper that John talked about yesterday was a really beautiful early experiment, and they had incredibly high visibility fringes, but the detection efficiency was still very low. So we're only sort of violating a shot noise limit relative to the resources consumed if you factor out efficiency and things like that. So we were interested, I mean, not only for metrology, but also for all sort of photonic quantum optics protocols that involve discrete states in one kind of another, to think about how we can improve detection efficiency, throughput in the system, source heralding efficiency, and so on, in order to do unconditional photonic metrology and other photonic quantum information experiments. So if you've been in the field for many times, you'll have seen, down converters that look like this, pictures in papers, where, you have some sort of, up conversion, which then means you lose some efficiency in the pump process. That's not so bad, although it comes back to bite you in terms of signal to noise in various ways. You have these critically phase matched down conversion crystals, which have these, I'll get this to work in a second. Here we go. There you go. I'm not laughing at you so much anymore, Austin. No, you have these frequency entanglement here, which you have to filter out if you don't want to introduce mixture. Then the shape of the optical modes is terrible. So coupling it into a fiber or some other sensible optical device is really low efficiency. If we want to put things in fibers, the loss of the fiber at the typical wavelengths that we used is terrible. And then silicon APDs in principle can be great, but in practice rarely are for certain important reasons. And so when you put all this together, you end up with sort of lowish purity and certainly low efficiency sources of photons. So in the mid-2010s, we and several other groups around the world worked on sources that improved these things. There's no up conversion here. We used periodic polling and careful phase matching to have frequency unentangled sources that don't need any or much filtering. The modes are spatially Gaussian or very, very close, so you can couple them very efficiently into your optical systems. It's a telecom, so low loss fibers, and superconducting detectors can give you, in principle, extremely high efficiencies. And so with all of this, you have very high purity, very high efficiency sources of photons. And so, this data from Sergey is probably not completely up to date, but, heralding efficiencies that take into account everything, including the final detection of, well, it says 82% there, but I think it's now up sort of above 85%. And, factor out 0.9 for the final detection efficiency, the source and the propagation and coupling is all extremely high quality, and the states are very frequency unentangled. And so this then allows you to do experiments like the noon state experiment, but in a completely unconditional way, as we did in 2017. And I mentioned this work because this is the last sort of, bit of serious work that I ended up discussing with John. I think it was at QCMC at 2018. We had a bit of a chat about it. So you've already seen from many people what these noon state interferometers look like. Here we're just thinking about a 2-photon noon state, the simplest case. And you have these fringes that work with, the fringes that have got, double the frequency of a single photon fringe. Okay, and so the resources are the number of photons in an interferometer in a defined mode, and that mode, for example, can go through a phase shift. Okay, so the trick, the physics behind all of this, for those of you who might not have seen it before, is simply that if you have steeper fringes, then some sort of counting uncertainty in the photon statistics translates into a smaller phase uncertainty. That's the kind of key idea behind things. And one can say that in the real world, it's not quite as simple as that, because if you have imperfect visibility, say from impure photons, for example, then those fringes shrink, and you can see that the maximum gradient decreases there. Or if you've got loss in the circuit, then if you sort of don't just renormalize everything, if you take into account all the photons that were lost as well and plot your probabilities correctly, then you can see that you end up with these smaller fringes, which also have sort of a smaller gradient. Well, one can analyze that properly with the Fisher information, as Peter and others have talked about. I'm not going to go into that today. I'll just flash up this heuristic, which is actually characteristic of some of the early papers that you guys were publishing. These kinds of things popped up in the first noon paper, I think. But anyway, the idea is that you can write down a formula for the quantum enhancement, which basically includes the heralding efficiency, the visibility, and the number of photons. And if you're in a particular regime, then there's an unconditional advantage. As I said, the Fisher information is a bit more fulsome, but this is the basic idea. And so these are the regime that we got into, and you can see that this heuristic tells us that we should be able to beat the shot noise limit with nothing brushed under the carpet. So we went off and did an experiment in this. It was all sort of polarization modes rather than spatial modes, just a one-to-one mapping. I won't go into the details. We saw the fringes. You don't see a 2-0 fringe there. That's because in this data, we've mapped together the 2-0 and the 1-0. So we've included all the cases where one photon could have got lost. There's no fringe where both photons got lost, but we did count those resources as well, carefully characterized, also higher order terms and the other things that you don't want to brush under the carpet. And we were able to see that in a particular phase range, we were able to beat the shot noise limit unconditionally. So that was nice to be able to discuss that with John as a sort of a wrap up of some of that noon work that we'd done, sort of interacting with him and his colleagues over the years. Oh, right. Yep. So the tapered blue is the scaled shot noise limit for the number of repetitions. So it's got that square root scaling. And the reason that there's got that fan out here is that when we actually, in order to do this, you have to, collect the statistics, and we calculated it taking into account errors. And this is like an error uncertainty. When you're calculating Fisher informations, as you know, when things drop to zero, then you've got these sort of. So yeah, all the shading is sort of, I think I can't remember if it's 1 or 2 standard deviations of uncertainties. Okay, whoops, forwards. All right, so I guess in the remainder of my time, I wanted to talk about something that's new, and that's in the spirit of some of the work that John had done in the later years. I mean, obviously, he was interested in the quantum internet, and we heard a lot about that from Peter Rode and others. And so one of the other applications that one can think about with these high quality sources of single photons and entangled photons is how one can go about overcoming the challenges of sharing entanglement optically. And the biggest challenge, of course, is loss, but there are other issues as well. And so this particular work was done, well, Sergey is the first author, but in collaboration with Tim, Ralph, and others. So a long time sort of theory collaboration on this topic, various different ways of looking at overcoming loss in entanglement sharing or in state transmission. Okay, so we're in the field of quantum communication. Here's John doing some kind of quantum communication. But the reason I picked this picture is because he's got the sunglasses on, and we can see that, the light that's going to go through them is going to undergo some sort of attenuation. And this is the thing with optics, right, is that it doesn't really matter whether you've got free space or fiber transmission. It doesn't matter what kind of encoding you have, whether you're using some particular kind of variables or some particular degree of freedom to encode your information into. Loss is a killer to a greater or lesser extent in all of these different schemes, okay? And so we need to sort of think about how we do long distance communication in the presence of loss. Okay, so in the rest of this talk, you're going to see this cat. This is Sergey's cat called Meloncello. So I've stolen these slides from Sergey, and his Meloncello is going to appear quite a bit to teach us about thinking about how we're going to use this heralded amplification scheme to overcome loss. Okay, so here's a picture of Meloncello, Melon for short, and we're going to send him through this lossy channel, or send a picture through this lossy channel, not the cat. We're not that good at teleportation. I'm a dog person. Maybe we should send the cat in. No. Okay, so I mean, I guess the thing is that if you break down this picture into bits of information, then we can try and send them through the channel, and sometimes they won't come through. And the simplest way that we deal with that is just post-selection, okay? We take the bits that did come through, and then we just repeat the protocol over and over. We collect lots of statistics, and finally we can reproduce a pretty high fidelity image of Melon here at the end. Okay, that's good, but and that's what we do in quantum key distribution over very long channels, but it's not great for device-independent protocols. So if we want to share entanglement, and in particular, if we want to share entanglement in a regime where we violate a Bell inequality or some other non-local inequality, this really high loss is going to do us in. So we need to think of something else. And there was an idea from Tim Ralph and Austin Lund to do this so-called noiseless quantum state amplification. Okay, this is from about 10 or so years ago, a bit more. And the idea is that ideally, if you have, say, a coherent state, alpha, what you'd really love to do is amplify it and make a bigger coherent state, G alpha. But you can't do that because the no cloning theorem won't allow that to happen. Okay, we have to add noise. So this always looks pretty bad, but I guess what Tim and Austin realized is that one can in fact make a probabilistic, and not just a probabilistic, but a heralded probabilistic amplifier, so that sometimes you can get this transformation that you want. You can take alpha to G alpha with some certain probability, and the rest of the time you get some noise that you don't want. But the point is there can be an independent heralding signal for that, as sort of shown in the cartoon on the right. And that then might be useful for certain kinds of protocols. Okay, in order to do this, we're going to have some sort of, pure ancillar quantum state coming in, and I'll say a little bit more about that in a moment. Okay, so the very simplest form of this kind of amplifier is using the quantum scissors that David Pegg and collaborators came up with, and that others have looked at over the years. You have some quantum state comes in, you have some ancilla comes in, there's a beam splitter with reflectivity eta and a couple of detectors, and conditional on some detection pattern in those detectors, in this case either one or the other clicks, then the output comes out with a gain that depends on this reflectivity eta here. Okay, so as you decrease eta, the gain goes up, but at the same time the probability of success goes down. Okay, I don't have a plot of that, but that's the price that one pays. Now, you can build more sophisticated versions of these. This works really well in the low amplitude regime. You need more sophisticated things in the high amplitude regime. But in any case, various demonstrations to different degrees of sophistication have been shown for amplifying optical modes, polarization qubits, path qubits, entangled states, and in a whole bunch of papers by us and others. All right, but this device by itself is still quite limited. And the reason is shown in this little picture. Here's Mellon again. Here's Mellon's picture attenuated, going through some loss. And the thing is that sometimes the amplifier works, but sometimes it doesn't. Okay, we get some ticks and some crosses. When it works, great, we've amplified our state, but when it doesn't, well, the information doesn't come through, and we'd still need to go back to this repeat and post-selected scheme if we just use the amplifier like this. So we don't seem to have gained much. But maybe you can see where this is going, which is that if instead of amplifying the information itself, we think about preparing entangled states, sending them through a channel, the amplitude of the states is degraded, there's some mixture introduced, so we don't have a strong entanglement anymore. But now we try and amplify this up, and then when that process is successful, we've got an improved quantum entangled state, and we can use that then as a teleportation channel. We can send some information into a Bell state measurement and teleport that over to the other end. Okay, and so this then starts to look like what you'd want to do in a quantum repeater. Okay, it's sort of a basic quantum relay that then one could build on top of with memory and error correction and other things like that. Okay, so then we can teleport the picture of Mellon through using successful amplified entanglement channels. Okay, so we did this experiment. Instead of teleportation, we used teleportation of entanglement or entanglement swapping. So in other words, we had an entangled state here, which was our initial one that was going to get degraded, and then we do entanglement swapping. And so then the idea of this is that without all this extra surrounding apparatus, ignore this and the stuff on the right, you'd have some entanglement that's degraded through the channel. And what we want to do is compare that sort of naive case with the entanglement that you get after this channel correction and entanglement swapping step. Okay, so is the red case better than the orange or beige case? Okay, that's the comparison to see if this sort of scheme works or not. Okay, so there are some requirements to do this in the lab and to actually be able to demonstrate it with high performance. The first one of those is that we need to efficiently deliver and detect the states that come into the ancilla, okay? And in this sort of simple version of the protocol, these are high purity single photons, okay? So we need to have those, and because they need to be high purity because we need to have high visibility Hongo-Mandel interference. There's a non-classical interference that's at the core of this amplifier. And also, by the way, at the teleportation step, but so we need that as well. And then we also need, as is always the case in these non-deterministic sources, a low contribution of higher order photon number states. And so achieving all of these three things at the same time maybe sort of sounds like it's easy as a theorist to write that down. In the lab, it turns out to be pretty hard to achieve all of that at the same time. So Tim patiently bore with us while we took a long time to get all of this working well, and then we were able to do some stuff. I should just give credit that the particular detectors that we use through a long time collaboration with Seiwu Nam's group at NIST. These are superconducting nanowire detectors that have very high efficiency. Now I think you can go out and buy similar detectors, but we've been collaborating with these guys for many years. And I've already talked about the sources and the efficiencies and the purities that they can achieve. That purity of 0.8 doesn't look very good, but with the sort of a modest, this source is simpler than some we've built, and with a modest amount of filtering, you can push that close to 1 without impacting the efficiency much. Okay, so we went off to the lab and we did this, and this looks like a horrible experimental diagram. I'm just going to show you in a very sort of simple way. The sources are not in the picture here, so the light from the sources is coming in. Look at the top there, you can see the image that I've already shown you. Here is where the two parts of the entangled state go, one to one side and one to the other. Here is, whoops, what's happened? Oops, okay. Takes a while to catch up. Yep. Okay, here is the ancilla coming in, and the other, yeah, and the amplified state going out to the right. Here is where the teleportation happens. And then the other part of the entangled state, we're sending across the final entangled state after swapping, we're sending across to the right, and we're going to compare them both in a joint measurement over there on the right-hand side. Yeah, so that's where the joint measurement's going to happen over there. You don't necessarily have to bring them together, but we do that. By the way, I should say that these are non-local single photons. The entanglement in this case is not polarization qubits. It's states like 1, 0 plus 0, 1. Ironic, given the entanglement-free reference in our previous paper, I know, but anyway, there we go. So I did know after all. Okay, so these are the actual heralding efficiencies that we get in different parts of the circuit, a little bit lower than our optimum numbers because there's a bunch of different components in there and a little bit of filtering, so 0.66, 0.69, so on. So pretty high. Independent Hom visibility, so this is between photons from two different sources. And it might not look like much, but if I can just sort of advertise for a moment, I mean, having a really high independent Hom visibility at 0.97 and simultaneously efficiencies of around 0.7 at the same time, there's very few groups in the world that are doing that sort of thing. So these are really kind of high quality quantum optics experiments with single photons and entangled photons. Yep. Okay, so we'll come to the results. Very quickly. Basically what we're looking at here is on the horizontal axis, we have the gain. In fact, it's the splitting ratio. So higher gains is to the left, lower gains to the right. And then on this axis, we're looking at the concurrence, which is the measure of entanglement that we're using. And these dashed lines are what one gets just through the lossy channel without any amplification. And then the red data points or pink data points are when one amplifies the state and teleports or entanglement swaps through the channel. Okay, so this is all done in a very high loss regime, and we're not completely correcting the entanglement. These are not becoming maximally entangled states after the correction. You need a much more sophisticated version of the amplifier to do that. However, except for the fact that we didn't do rigorous timing and use a quantum memory, so that is a caveat here. But other than that, this data is unconditional. Okay, so it's almost it's conditional, but not in terms of you know, the noise and the photon part of the picture. only in terms of the timing and the memory. So this is a sort of a genuine enhancement of entanglement through the channel. Okay. Yep. No. Yeah, no, the gain, this is, it's not a gain. It's actually, what I would say is gain beam splitter efficient, like reflection efficiency. So that's then related to the gain by another formula. Okay, so I mean, it's a sort of crazy, 1 minus eta over eta relationship. But the key point is that high gain is this way to the left, and low gain is to the right. And because of higher order terms and noise and things, you can actually saturate the gain and it falls off. So I think in the ideal case, we saw in the previous plot that we expect the gain to sort of keep rising up to infinity, although with the increasing or decreasingly low probability of success. But in practice, like in many experiments, noise finally bites you on the bum and you don't quite get there. Okay. Yeah, I'm about to wrap up actually. So thank you. All right, so if you want to read any more about this, come and chat to me about it. But I suppose I want to just finish with the reflection that what John sort of contributed to me as we took this journey through photonic quantum optics is just an enthusiasm for the field, just an interest in all different things, not only quantum computing, but also, metrology, foundations, which I haven't talked about, but I've done a bit of that with Howard and others, and these quantum loss tolerant internet protocols and things like this. And what the niche that we've tried to occupy there is doing these unconditional or high performance experiments. So there's many collaborators that I should thank. I mean, Howard, Tim, and Dominic are some here, but many others as well. So thanks to all of you. And yeah, let's celebrate John through all this stuff. Thanks very much.
Thank you so much. That was great. We have plenty of time for questions. Let's start with Gavin.
So I remember when discussing John actually why this last thing with big laser because photon signal, but then like the counter example we discussed was sensing with some like mild, very sensitive to light killing. Has there ever been realized, or do you have any ideas of what would be good application?
Yeah, it's a fair comment. I mean, you're absolutely right that if you've got enough photons, the shot noise limit is actually pretty darn good. So that is one way of solving these problems. And the counter example is to say one of two related things. One is let's just explore the fundamental limit. So how much can you get kind of per photon? And then the applied version of that is, yeah, well, we're going to do something bad if we have too many photons, like destroy a molecule. Now, the irony of the molecule example is that most of those biomolecules are not that sensitive. Actually, sure, you can put too much light on it, but 2 photons is still orders of magnitude below what you can do, right? And we can't make 100 photon noon states. So probably with a biomolecule, you're still going to be better blasting it with a laser. We could think, though, of applications in the security space, right? So let's say you're trying to, measure some phase shift in a way where you don't want to reveal the presence of the sensor to an adversary. Okay, so maybe you're measuring the phase shift when the glass vibrates because somebody's speaking and you're trying to pick up their voice. You don't want the person who you're eavesdropping on to know that you've got a laser shining on their windows or a noon state or whatever. So you want to try and extract the maximum information per photon. And so that prompts you to push beyond the shot noise limit. Now, as we know, squeeze states are one way to do that. But if you're thinking about, photonic or discrete photonic states, then noon states are the best you can do, except that they've got this sort of poor tolerance to loss. And so then you think of Holland-Burnett states and the other things that John and many of his collaborators have looked at. And we do have work on Holland-Burnett states and stuff as well, but didn't present it today.
Have we got any other questions? Okay, I have a simple one. in the previous experiment you were talking about with the error corrected channel, can you give me the essence of what's going on? Because the way I would picture it is you have, half of your entangled pair going through some lossy channel. At that point, the entanglement's been degraded and you're doing a local operation, but you're seeing some improved performance. So what's actually going on there?
Yeah, I mean, I think what's happening is you've got this conditional heralded operation. That's what's going on. So you're essentially attempting to amplify the signal, and usually you would add noise, but it turns out that the insight that Tim and Austin and others had is that you can sort that amplification into cases where rarely it's successful, but you can bin those from cases where you just completely stuff the state up. Okay, so it's this sort of heralded amplification case, and you use the independent signal to sort out those cases where you've amplified the thing or you've boosted the signal. It's a bit like an entanglement distillation kind of process. It's non-deterministic, and in fact, any purification step has to be non-deterministic, right? So you just, what the trick is that you're able to sort the successful cases from the unsuccessful.
I see.
cases.
So you're making the entanglement more resolvable, but in some sense.
In some.
Okay. All right. We have time for a few more questions if anyone's got one, but if not, let's take it.
Yeah. Okay, so in the sort of early versions of down conversion that you see, you end up with this process that's critically phase matched to conserve momentum. So you've got this birefringent nonlinear crystal. You shine the light in, and then you get these kind of often cone-shaped regions of down conversion. Now, it's true that if you sort of pick a particular frequency, then kind of across the cone, there will be some sort of Gaussian profile. So in some sense, it does retain some of the properties of pump, but it's something like, I can't remember exactly, but it's something like a convolution of the pump shape with the phase matching function. And so it turns out that without sort of significant filtering, you're always going to, well, to get the right shape, you need to do some filtering, whether that's just coupling into a fiber or something else. And when you're filtering, you're throwing away light, which means your heralding efficiency drops. Now, in this sort of collinear case, it turns out that the particular phase matching conditions, depending on the focusing conditions and blah, 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 it's quite complicated actually. You end up with something that's almost exclusively in a Gaussian mode. And that's just a particular, you have this extra degree of freedom to tune things because we do this quasi-phase matching with a periodically poled crystal. And indeed, it doesn't even have to be periodically poled. You can orient the domains sort of and there's a whole story around that as well, which Nora or I can tell you if you're interested. But the short story is that without too much work, you can get something that's a good approximation spatially and not quite so good in the frequency domain, but it's still not bad either. Yep, I agree. Yeah, that's right. So, I mean, at the end of the day, your success probability is ultimately limited by essentially something like a state discrimination protocol, right? So it's basically like you've got a pair of states, they've got a certain overlap, and they have a certain distinguishability. If you sort of amplify the distance between them, then the probability has to be such that you don't really win through that process, right? So that's the ultimate limit. Now, this particular kind of amplifier I showed has a probability of success that falls off worse than that ultimate limit, as it turns out. But in principle, yeah, it is. You're right. There is a fundamental limit through distinguishability, I think, is the ultimate one. That's correct. Yeah, it can be perfect. I guess I think about the noise in the fact that what you're really doing is when it fails, you have a state that's very noisy. Okay, so if you sort of think about the complete state, probability, the successful part, which you've heralded out from the unsuccessful part, then overall that noise doesn't go away. What you're really able to do is bin the noise. So as Howard says, you bin it into a case where there's none or no added noise, only the noise of the initial state, you know, on the ball and stick diagram, if you will, and then another state, which is your failure, where all the crap is.